This is AP Calculus, Lesson 7-1. Let's talk about our unit, which is not pulled up here quite yet. Let me come back to Unit 7, our unit guide. Our unit guide is 5 lessons long. We have 6 self-checks, which is 2 more than normal, so we'll have a whole another day of self-checks, and then everything else is normal. So today we're talking about motion application, specifically motion differentiation. So, types of motion. And this is awesome because we have the BC girls in here. You're going to see the difference between AB and BC. In AB, so I'm talking to the 3 of us in AB, you only have to deal with horizontal motion and vertical motion. Let's write it down. Horizontal and vertical.
Just don't do it. I remember when we were learning this in AB, it was like so cool. Like I was like very interested. Like it's like, you know. But now in BC, I'm just like.
So this would be your X, this would be your Y. And then BC, you do them both at the same time. Both at the same time. Or both together, I guess. And it's hard.
The funny thing is we didn't even know that because we're not learning anything from this class. Sorry, continue.
So that's when you do a parametric curve, where you do a vector-defined function, when you do a polar function. These girls have already done that. They know how to do the derivative of a vector-defined function. You can also do the derivative of a parametric motion. So parametric motion, where you actually have an equation for x, you have an equation for y, and both of those equations are in terms of t. And it's a fun thing to do, but it is difficult. It depends on what you study in college.
I'm studying music theory.
If you study music theory, you will not have to do this for college. If you study anything sciencey, at all sciencey, you will probably do this in college. Engineering is very sciencey. You will definitely take you'll definitely figure out what the derivative of a parametric curve is or something like that. All right, so describing motion. When are you 2 girls from BC Calculus? Are you in physics right now, or you took physics last year?
We took physics last year.
That means you're taking physics.
No, we're all in I was supposed to take it this year, but because I only took chemistry last year, I can't take it.
So you're taking physics next year?
They will, like, physics is not offered this year. They will take physics next year.
So Rochelle just missed it. Okay. So this is going to be super applicable to physics. So, and this is how they describe it in physics. Position. This is your x or y coordinate depending on which direction you're going. So this is your x or your y. If you're going up or down, obviously you're going to be dealing with y. If you're going left and right, you're talking about x. And position, almost always, this is going to be your distance from the start. Distance from the start. And usually the start will be 0. This can change if they ask you the total distance traveled. That will be the absolute value, because if I go forward and backward and I end where I start, my position is 0, but I've traveled more than 0. I've gone forward and backwards, right? So that'll be challenging in this unit, but we'll get there. Velocity. So we talked about v when we're talking about velocity, and that is how fast this position is changing. The speed, the rate of that position change. So let's just say the rate of position change. Position change. All of today's lesson, by the way, is talking about how each of these 3 things relate to each other graphically. So we're going to be analyzing graphs for the lesson, graphs for the homework. And acceleration, this is the rate of the position change, or you can just think of this as the rate of velocity change. And I told us before, whenever I ask for a rate of something, rate of whatever, I'm really asking for that keyword, that magic word that starts with a D. Rate of anything is the blank of that anything. Derivative. Exactly. Which means, yeah, there it is. That means velocity is the derivative of position. That means acceleration is the derivative of velocity, or the double derivative of position. And yeah, ta-da. Let's go ahead and look at some examples. So on this graph, I want to graph a point at 1, 4 at this intersection, 2, 8, 3, 12, 4, 16, 5, 16, and 6, 16. And there are going to be 2 lines that I want us to draw on this one. So let's draw 2 lines first line, second line. Second line goes and continues on and on forever. This goes on and on forever in that direction. All right, so let's say that we were talking about a car in this case. Things that have wheels are nice and continuous. If I'm talking about walking, then I am discontinuous because I'm taking steps, or a frog hopping, that's discontinuous. But if I have wheels, it's nice and continuous.
If you're walking, you're still moving at a fairly constant rate.
Fairly constant, but it would look more like this than a straight line. So wheels are nice and straight when we're talking about the position. All right, so by the way, let's do a little bit of a review from last unit, or 2 units ago, I should say, when we did piecewise functions. What are those 2 functions that I just defined here? Let's say that x is a function. X is our function with respect to t, with respect to time, and that's equal to the piecewise function of what? Let's get a little bit of review in there. What are those 2 functions? There's this one function right here, and then the other function that starts after 4. So what's that first function? What's the slope and y-intercept? It is linear, yep. No, it's not x, because that would be right 1 up 1. It went right 1 up.
So it's 4x?
Yeah, 4x, or 4t in this case, because our variable is t, and plus 0 because our y-intercept is 0. And that's for what values? For where t is between which values? Between where and where? It doesn't exist right there. It doesn't exist right there. It only exists between 0 and 4. So t is less than or equal to 0, less than or equal to 4. And then what is this other function? Someone aside from Rochelle. What is this function right here?
It's just t equals 16.
Or x of t is equal to 16, yep. And for what values? For between what 2 values?
-4 and
Yeah, between
no,
4,
sorry.
4, not -4, yeah. Between 4 and it goes on. We can just say for 8, I guess. It might end at 8.
T is greater than 4.
Yeah, and it doesn't need to be, it could be greater than or equal to, it doesn't really matter. Or this should say less than or equal to. 4 is less than or equal to t, or t is greater than 4. It doesn't matter either way. All right.
Does only one of them have to be?
Usually one of them is equal to and the other one is not, just as a way that most mathematicians do it. I'm not exactly sure the reason why. Maybe I need to meditate on that. All right, so my problem, my task for you right now, can you visualize what the graph looks like for velocity if I just gave you this graph of position? What does the graph of velocity look like?
It would be a
Okay, and I'm going to pause you right there, Ben, because not everyone thinks quite as fast as you. I'm going to pause for 10 seconds. I want everyone to think in their heads what it looks like. Can you see what the graph of velocity looks like? All right, that was 10 seconds. How many people roughly see a graph in their heads by raised hands? Okay, cool. Who wants to volunteer to tell me what that graph looks like?
I can say one of the problems.
Okay.
Well, for 4t, it would be 2t squared, right? I mean, 2t to the power 2. No?
You're going the antiderivative. I'm just saying you just take the derivative.
Oh.
So, and you're already thinking about the equation, which is definitely a crutch to help you figure out what the graph should look like. But you should be able to just look at the graph and go to the next graph. Look at this graph to see roughly what's going to be happening in this graph. To get exactly like the difference between here and here, yeah, you'll have to actually take the derivative. But roughly, what does it look like? Arrow, Ben, you want to take a guess?
the constant function.
Yeah, it's a constant function. It's a line function. And it happens to be the constant function of 4 because we can take the derivative. So it's just this flat line here. And we'll change the color here. It's this flat line at 4 up until where? Where do I stop this line? Yep, at 4. Good question. Why 4? Someone else answer. Why do we stop there instead of going on?
Because the slope changes in that first block.
Yeah, so this had a constant slope, and then all of a sudden right here it changes, and it's also defined all the way up to 4 in terms of the piecewise function as well. Okay, and then what is the rest of the graph look like? Does it go down like this? Does it just drop off like this? Does it curve down? What does this look like over here from 4 to 6? What's going on?
I would guess it would curve. The slope would be down. It would go from 4 to 5 and then go down to the negative.
Oh, and then it would keep going negative, so it would
Yeah.
keep going down like this. Okay,
That'd
Yeah.
be my guess.
good guess. Aaron, what do you think?
0. It's just.
Yeah.
Just 0. So is it like the flat line, the constant function of 0? Is that what you're thinking? Sure. So something that looks like this. Ben, what do you think?
Yeah.
Yeah, and it is that. So let me go ahead and make my line here. It starts from 4 and just goes to 6 and goes forever and ever in that direction. So this arrow goes forever and ever in that direction. And it's weird here. We have this discontinuity now when we're looking at the derivative, because you can't just jump down. So you have to do this open dot to say, at the value of 4, you don't actually know what's happening.
They're both open?
Actually, this one should be closed according to how we've defined the piecewise function up here. So let's go ahead and define the piecewise function here. So what variable am I using? It's not x of t anymore. It's something of t. What am I doing?
Using that it's like x of t.
Yeah, it's the position. So it's either x or y of t. This one is going to be what of t now? It is v of t. And that's going to be equal to the piecewise function. What? Now you're just taking the derivative of the top, take the derivative of the bottom. Take the derivative of 4t. It would just be 4, and then it's for the same values. For 0 is less than or equal to t is less than or equal to 4, and derivative of 16 is 0, and for the same values, for 4 is less than, t is less than or equal to 8. Sure. And that makes sense with our graph too, because this is the constant graph of 4, that's a constant graph of 0, that's a closed point and an open point. All right, now, can you visualize without using these, without looking at the piecewise function, just look at the graph, only the graph. Can you get from the velocity graph to the acceleration graph?
Would there just be one line?
Just one line, and like a one flat line like that?
Yeah, it would
Okay.
be at 0.
At 0? What do you guys, okay, so that's Rochelle's idea.
Yeah, I think so too.
Everyone agrees, and that is the right answer. Yeah, you guys have it. So it is just this flat line down here at 0. That's a little bit too low.
Would it keep going or would it stop at 4?
Ooh, that's a good question. So I'll leave this open right here, and we can decide that together. What happens at 4?
Oh, wait.
Okay, so should there be an open point or closed point at 4? Closed point.
Oh,
Yeah, because they actually end up matching. They're both 0, because we can actually look at the acceleration
but that would be as if.
with respect to t, and that is equal to, that was a horrible curly brace. Curly brace, what are our two functions? 0 and 0. Yep, 0 and 0, and for the same values. And I guess we don't really need a piecewise function anymore, do we? We just can say a of t is equal to 0. And we can, since we defined it, we can say for 0 is less than, t is less than 8. And there it is, yeah. So I just made it up. I just decided that we would end at 8. If I said that it went on to infinity, then the answer would just be a of t is equal to 0 for all values of t greater than 0. Yeah, so just being able to jump from the position graph to the velocity graph to the acceleration graph, and eventually backwards also, going from acceleration backwards to velocity, if you have some initial conditions. That's what I expect us to be able to do in the homework. Any questions? That's it. All right, go ahead and write your summaries.